Today we are going to start section 8.2. So first, let's look at the book. And this is the first page, which was scanned earlier. And we will, but nevertheless, focus on the top and the bottom a little bit. Mostly, yeah. All right, that should do it. Next, page 264 and 265. Let's see. Okay, that looks about right. The whole page, and then the top. And then the bottom. Okay. And finally, 266 and 267. Let's see. Okay, there is this thing here. Okay, and then a little closer on top. And then on the bottom. All right, that should do it. So let's look at page 263, the indeterminate form of infinity over infinity. So we have finished the 0 over 0 problem. Now the next question is, what if we have infinity over infinity? That can, we can manipulate it to make it turn it into 0 over 0 by doing the division. Okay, stick a bunch of divisions. So here's our original formula. We'll stick a bunch of, we'll flip it around, okay, do some division manipulation, and then it turn it into 0 over 0, and then work it that way, right? But the problem with that is that gets really, really weird. It can get more complicated, and such that each function becomes even worse, more complicated than before. So does L'Hopital rule apply without us having to do this? Can we just simply do, in the infinity over infinity case, can we just do this anyway without doing this silly manipulation over there? That is the question. Okay, now so let's go to the next page. Now let's see, if this limit exists, then it does work. That is, if you work out the division. Where is it? Let's see. Is it this one or this one? This one. Okay. If the limit exists, then this thing, if we let b equals to this and a equal to this thing in the equation 2 on the previous page, this b does end up being equal to a. So please work that out yourself. Okay. It does, but that's only true if and this is only true if the existence of A implies the existence of B. So does it imply it? And that's what we're going to consider. Okay. So yeah. So please work out the algebra there. It's it should be pretty fast. Although yeah. And although it's not immediately obvious, just slap the fractions around a little bit, and you will get it to come out. Now, so let's look at subsection 2.1, L'Hopital's rule. We're going to prove something first that is got to do with one-sided limits. Theorem 4. Okay. Now f of x, f and g is C1. That's fine. But this time, notice carefully that x is good. This is only true for x goes from a not including a. Okay. That part matters greatly. It doesn't have to include a. So it's only C1 up to a, but not including. And then the other side is b or whatever. We don't care about the other side so much. So this, and then the limits both go to infinity. And then g is not 0, but only up to a, but not including. G can be 0 at a. Okay, that would be okay. And that matters greatly. And then the fourth condition is that the limit of the derivatives are equal to a. A could be plus or minus infinity, but the derivative of the limit exists. If that is true, then the limit of the fraction itself exists. Okay, so the derivative has to exist first. Yeah. if that is, it can even equal to infinity, and it's still called existing. If it's just wobbling back and forth forever and doesn't ever stop somewhere, then it's called not existing, okay? Because it's not even going to infinity. Going to infinity at least is something. It's going somewhere. This is going nowhere. It's just wobbling back and forth permanently. So let's look at the proof. As in proof of theorem 3, we have this equation 6 situation here. Okay, that is, let's look at this equation for a second. We have fy minus f of x, which is f prime of psi times y minus x by the MVT, right, the mean value theorem. Similarly, gy minus gx also equal to g prime of psi times y minus x. Give me a second here. Now notice that this isn't just the MVT. This also comes from a previous page. Please look at page 260, where theorem 3 is being proved. Right here, it comes from this equation. That is, the difference in f is equal to f prime times of psi. Psi is the stuff inside, and the difference in g is equal to g prime of psi. Notice it's the same psi. Okay, that's the part that I wasn't noticing at first, but it did work out that it's the same thing. The identical psi. We don't have to pick a different one. So if that is the case, so we have this. Okay, and this of course is equal to that if and that is the same as this thing, which the only difference is we factor out the f over g, and then the rest of it is in division form. Okay, so in other words, this equation is the same as this equation if you multiply it out. All right, so far so good. And with in the meantime, psi is between x and y, of course, and by the MVT principles. Now please pay attention, okay? Because now we're gonna do something super odd, and now what did the book call it? Novel. We're gonna do something novel. Now the novel thing is that we're gonna let x and y both approach a, which is fine. Remember, a is the one side, right? The left side. However, x making the approach much more rapidly than y. Okay, now I'll say that again. Pay attention to this sentence right here, where it says that, so x and y are both going towards a. So a is up here, right? It's the left side where we're approaching this whole time. A is what we're looking for. But we're gonna approach a, but x will be making the approach much faster than y. In such a way, the limit of fy over f of x is going to be 0. Why? Because f is going, as x go to a, f is going to infinity. But if you make sure that x goes to f of x goes to infinity much faster than fy, then this limit will be 0, okay? Because x is way ahead. And so it's the same function, but they're both going to infinity, but one's a whole lot more slower than the other, to the point that the limit of this thing, you can force the limit to be 0. And the same with g, same for the same reason. So we're going to choose it that way. Now the book is not explaining how we're going to do that. So I have written down one way of doing it. How will we choose it in such a way that if such a way that f of x is going to go to infinity much faster than f of y, such that the limit has to go to 0. One way we can do it is, let's pick a bunch of y's equal to dk. D is just some variable I picked, and let's say dk is a sequence that approaches a as k goes to infinity, but dk is not a. Okay, so dk is a convergent sequence that goes to a as k goes to infinity, but each member does not equal to a. And then, so that's good. And next, we're gonna, for each dk, so fix one dk at a time. So for each dk, we're gonna choose a ck that is even closer than dk. But ck is still not a, okay? It's just closer. In such a way that f of dk over over f of ck is going to be less than 1 over k. the reason is because we choose ck such that fck is so much bigger. See, remember f is going to infinity, so that's totally possible because we start out with dk, then we hold on to it, okay, and not let it move, and then we pick ck that's much bigger in comparison to dk, and we do this for each k as k goes to infinity. So we have a bunch of ck's that's much closer than its corresponding dk, in such a way that fdk over fck is less than 1 over k. And the same for g, okay? G of dk, we can also choose such that g of dk over g of ck is also less than 1 over k. So at this rate, then as the limit as k goes to infinity of f of y over f of x, being that y is going along in the dk order, right? And x is going along the ck order, and as k goes to infinity, then the fraction is always less than 1 over k, which means it goes to 0, and same as g of gy over gx. And that's how we can arrange this novel trick that we've been introduced. All right, so now that we have figured that trick, so we have this sentence right here, okay? So now we have the limit of fy over f of x divided by f of x is going to be 0. Well, as y and x going to infinity at a different rate, x going to infinity a whole lot faster than y going to infinity. Going to a whole lot faster than y going to a. Okay, so now that is done. So as x and y go to a, since psi is between x and y, so psi also has to go to a. So then now the next step, what we're going to do is look at this. What we're going to do is take this equation. We're going to take the limit of f of x over g of x in this equation right here, okay? And then put this fraction on the other side of this. And so that it becomes the limit of this is equal to the limit of that, okay, times the limit of this thing flipped around. So now it's g divided by f. And this equation holds. And so what happens when this equation holds? Take a look. And this thing is going to 0. These things are going to 0. We just said so, okay? Each one of these things are going to 0. So that is just equal to 1. And that gives the limit f over g is the limit of f prime over psi, limit of f prime psi over g prime psi. And as psi is approaching a, so this limit is equal to condition 4, right? And which is equal to a, which means the original fraction is equal to a. And a can be positive or negative infinity, doesn't matter. They are going to be equal. So that is done with this neat little proof with a novel feature. And now I got that sentence from the next page. Look at page 265. Where the author says, since the proof has a novel feature, see, that's where I got the word novel for that trick that we just pulled. The use of the two related variables of x and y, so we'll come up with some example. Let's say g of x is 1 over x and f of x is log of 1 over x. Now then both functions go to infinity, right? And now for g of x, we're going to figure out some way to make it such that gy over gx is going to approach 0. To do that, in the book, the trick is to choose x equal to y squared. If x is y squared, then you plug it in, and then gy over gx does equal to 0. So please work that out yourself. Okay. Now I have done it right here. It's not that big a deal. You see a couple lines, so please confirm that information. Okay. Now, so gy over gx does go to 0, but the same trick, setting x equal to y squared, however, isn't good enough for f. Okay, f is not going to 0. I mean, f1. If you did that, fy over f of x doesn't go to 0. So we need to come up with a better trick. And the better trick is letting x equal e to the power minus 1 over y. If we do that, then things do work out such that the limit of fy over f of x does equal to 0. And this picking at y and x, of course, depends on the functions f of x and g of x. Now I have done the f of the F1 here, okay, and to confirm what the book says, that y equal to x equal to what, y squared or something. Yeah, it doesn't work for F, so we pick a different one, and you see that it does work or something. Yeah. Anyway, it does go to 0, and there's the graph for it. But anyway, so it does work. Okay. So that is, in general, then we have to, for each function, it depends on the function that we have to choose a bunch of x's and a relationship between x and y such that we can make the fractions go to 0 and get what we want. So that is that. Now next, let's look at the middle of the page, continuing. At first, it might seem like the theorem is illusory. What's illusory? It means it's pointless. Okay, why? Because the theorem just says that give me a second here. Okay, the reason it's illusory or pointless or is that because we are the function is going to infinity anyway, right? If it's going to infinity, then its derivative is also going to infinity. So we're just going to end up with infinity no matter what, even if we take the derivative. So what would be the point? Well, however, that is true. And in fact, we're going to prove that in problem 15 in the homework. However, that doesn't change the fact that the theorem is useful, because once you take the derivative, there's a chance that you might be able to cancel something out. Okay, and then so then everything, so that you can find the answer anyway. Whereas, and also taking the derivative may, quote, decrease the strength of infinity. Okay, right here. And we're gonna make the strength of the infinity go down or something. Right. So anyway, what that means is how the strength of infinity just means how fast is it heading for infinity. Is it going really fast, or is it just crawling along like log of x or something? And also, yeah, I should remind you that anytime you see log in this book, that means the natural log only. Okay, we don't care about base 10. So that is so anyway, the limit as for example, as a case in point, please work out this problem right here. When we do log of x over log of 2x taking derivatives, it's still going to infinity, but it also happens to be able to cancel out very nicely to give us 1. So that is good. All right. So that is so the next thing we need to say is that hypothesis 3 is not a consequence of hypothesis 2. That is, just because you might think at first without much thinking that if something is going to infinity, then the derivative would not be 0, right? It would just be crawling up. But not necessarily. Some functions will crawl up and go level, and then crawl up again and go level, and just keep doing that. And especially functions that has the sine or cosine in it. A case in point, right here. Okay, take a look at this thing. This thing is a function that is going to infinity as x goes to 0, but it also has a wiggly factor. See, there's a wiggly factor. You know how sine wiggles up and down, and then so its derivative also has a cosine in there, which also wiggles. So then even though g does go to the infinity as x goes to 0, g prime is 0 a lot in. As it goes up, it just keeps leveling a little bit and then keep going. In fact, g prime, the part of g prime, which is the part of g prime that looks like this, okay, is equal to, if you plot this thing, it looks like this in the computer. That's because it wiggles up and down infinitely as it approaches 0. So then that's why hypothesis 2. And that's why just because something is going to infinity doesn't necessarily mean that its derivative is always positive or bigger than 0. All right, so next let's do example A. Example A, I think, is very simple. So please do that yourself. Well, it's short anyway. I don't know how simple it is. Example B, I think, is the same way. Yeah, so here's example B. Which is right here. So please do that yourself. I think it's a straightforward calculation of some sort, similar to what we've done in basic calculus. And then next page, example C. Let's see. Well, of course, example B does depend on whether alpha, x to the power alpha, whether alpha is positive or negative, and but as it turns out, it makes no difference at all. Okay, that's how my proof goes. Since my proof doesn't care if alpha is positive or negative, I just went ahead and say, well, it's all less than this thing anyway. So that's how I proved it. But the book make more detailed discussion of what happens when alpha is negative. So please read this yourself, okay? All the details of that is when alpha is negative, it's not indeterminate. That is, you don't even have to apply L'Hopital's rule, okay? Just crank the whole thing out or something. And then so please read this part yourself, and we're going to move on to example C, where we have a similar problem where there's a bunch of alphas in there. And so please do this also, okay? This is for alpha and beta is bigger than 0. So please do that. And after you do it, and now read this paragraph where the author discuss what happens when alpha and beta are like less than 0. Well, what happens then? And there are some details that is not that exciting. Okay, and what happens, of course, when alpha or beta equals to 0, and so on. But anyway, so that's some details. Please read those details yourself. It's just a matter of paying attention to the signs and stuff. That's example B, and then next, example C is did I just talk about? Yeah, I just talked about example C. So. Here's what I did for example C for when alpha and beta is bigger than 0. I think the answer is pretty straightforward, not much tricks in there. And that's that. So please do that yourself as well. And read the rest of what the book says about all the details of when alpha is less than 0 or beta is less than 0 or somebody else is negative or something. And then so that's that. And then let's then move on to example D. Now example D is an example where this problem where the L'Hopital's rule does not work. Okay, and the reason it does not work is an example of showing. Well, first let's look at it. Okay, the problem is very easy to do. You can do it in your head how this is done. The limit exists and it equals to 1. But if you apply L'Hopital's rule, even though it is an infinity over infinity situation, if you apply L'Hopital's rule, the derivative is going to wiggle around forever, and the derivative, the fraction of the derivative does not exist. So we wonder, why is the L'Hopital's rule not working? That's because the L'Hopital's rule, the fourth hypothesis, says that the derivative has to exist. Okay, if it doesn't exist, then the whole theorem is not going to apply. So the derivative existing is part of the requirement for the L'Hopital's rule. And in this case, the derivative doesn't exist, so we can't use it. But we can still calculate the limit some other way. Okay, in this case, a fairly simple way too. So that has brought us to the end of this section. For homework, let me write it down first. So for homework, please do page 267, problems 1, 2, 3, 4, 5, 6, 7, 8, and then 11, 12, 13, 14, 15. That's yeah, that should do it. So let's look at problem 1. Problem 1 is, okay, I think is, problem 1 is fairly straightforward, I believe. You just take the derivative of stuff or something, and the answer comes out nicely. Problem 2, similar, we have to break it into two parts, where one part it goes to 0 and the other part goes to 1. And as a result, then it's equals to 0. So that's problem 2. And let's see. Yeah, and I also have a graph. So yeah, the one part goes to 1, and let's see. That's problem 2. Did I even plot this thing? Yeah, I did. Okay, here is it goes to 0 as see with limits we can always confirm our answer in the Desmos graphing calculator, when I plotted this thing in there, see, the graph goes to 0 at 1. Okay, so that confirms our answer, being that problem 2 doesn't have an answer at the back of the book. Now problem 3 is a similar deal. We have, well, actually I don't know what kind of deal it is, but anyway, we take the derivative and everything come out nicely. This is for x bigger than 0, and then for x less than 0, we do this similar matter and with the absolute value, and then the answer is the same thing. Come to find out, the graph looks like this and is symmetrical, and I have plotted the graph in the Desmos calculator. The answer is 1/2, but that is in the back of the book, so that works out. See, this is problem 3, where they converges on both sides. It converges at 1/2. Okay, I didn't mark this as 1/2, but it is. Up here is 1, so that is 1/2. So that is problem 3. Okay, next let's look at problem 4. Problem 4 isn't even indeterminate. If you plug stuff in, is minus infinity over pi over 2 or something. So then that is going to be minus infinity. Okay, and yeah. Anyway, it's just as x approaches 0 plus. You have to, this goes to positive, that goes to negative, so it's minus infinity. I don't know why the book specifically asks, is it positive or negative infinity? Well, it's negative infinity is what I got. And so that is, which is also correct, because that does have the answer at the back of the book. And that is problem 4. And next, problem 5, we have another odd situation. So we will we don't even know what the top add up to be. It's sort of an infinity plus infinity situation, so we don't even know what it is. So we're going to break this into 2 limits, and luckily the second part of this thing is the same as problem 2, which is equal to 0. So we know this is equal to 0. We only have to work on this thing, so that makes it a bit easier. So calculating this thing, there's a pi x over 2 and there's a pi of x, which is annoying. So we're going to change everything into just into the same thing. Okay, get rid of the over 2 bit by using the formula for the tangent half angle formula right here. So plugging that in there, so we have the tangent half angle formula. So everything is pi x, which makes it much better. And after some cancellation, we get the answer as -2, which is correct. And problem 5, I also graphed it in the calculator. And as you can see, as problem 5, okay, when x goes to 1, a positive 1, then the function goes to -2. See, it says right here. Now maybe I can make it look a little bigger. There. Yeah, see? See, the function goes to -2 as x approaches 1 from the positive side. So that is confirmed, as well as I think that also does that have the answer at the back of the book, problem 5. No, it doesn't, which is why I plotted it to make sure that my answer checks out with the calculator. So that is so the whole thing. Then the whole thing, of course, that we already said that this thing is 0 and that thing is -2, so together it's -2, and the graph is plotting the entire deal, right? So it does, and the answer is confirmed to be a -2. So next, let's look at problem 6. Problem 6 is 4, 5, 6. All right. So problem 6, we have a situation where it just the answer, we take the bunch of derivatives, and then tangent goes to secant squared, which goes to well, it eventually got here. Okay, and then after we rearrange terms, it becomes with just x on top, so which gives it at a 0 over 0 situation. So we can continue to take derivatives, got here, and by now this goes to positive infinity. And there's a and the graph, I graphed it, but I should put it here because I think this answer is in the back of the book. But the graph does show that the function looks like this. It does go to infinity. Well, when x goes to pi over 2. It goes to positive infinity. And that's problem 6. Okay, next let's look at problem 7, which is infinity over infinity. We take the derivative, and then stuff cancels out nicely, and it goes to positive infinity. If x goes to negative infinity, that this thing is not even indeterminate, because it becomes 1 over 0, which then automatically goes to positive infinity. And I have plotted the graph here, okay, and a hand-drawn one. I did draw it on Desmos. I just didn't want to bother making a copy of it. Well, the point is both sides go to infinity, whether the function is going to positive or negative infinity. And so next, problem 8, which is you have to worry about if alpha is bigger than 0, then this thing goes to infinity. That comes out pretty nicely. If alpha is less than 0, something happens. Please read that yourself. I don't really like to talk about negative stuff, and you have to, well, a bunch of details, okay? So paying careful attention to the details. I should be right unless I messed up anything. But if I did, you know why. But anyway, so let's just say that is correct. And anyway, so next, let's look at problem 11. Now, problem 11 has a trick in it, because if we do this, we've been doing derivatives, right? So this is infinity over infinity. So if we blindly take the derivative of this, it got here, still infinity over infinity. Take derivative again, and now it got here. And if you don't look carefully, you don't notice that this is undefined, because now at this point, then because this is 3 cosine x, that means the denominator can be positive or negative as x increases. So it swings up and down forever, okay? So the derivative is undefined, so we can't use L'Hopital's rule. So we need to use a different trick. So the different trick is we just use the old trick of when we have fractions like this, we divide the thing out. So divide by x squared, so this becomes 1 minus 3 cosine x over x squared. The top has just x left. So that goes to infinity. That works the same way as just y equal to x, right? That's just like x, because this part goes to 0. So this thing will go to infinity. And for x go to positive infinity, and it goes to negative infinity if x goes to negative infinity. And that's problem 11. And let me show you the graph. Yeah, see, problem 11 just looks like y equal to x, because that's what it is on the big scale. Okay, in a grand scheme, this thing doesn't matter at all when x is, say, a trillion, right? So then this just ends up looking the same as x, except for next to the origin, then it does weird stuff, as you can see the blue line here. But we don't care what it does. We don't care about the origin right now, so we only care about infinity. So on positive infinity, it goes positive, just like x, y equal to x line. And when x goes to negative infinity, then it goes to negative infinity. So next, let's look at problem 12. Problem 12, we have, we have this thing. Then now we have an integral sign inside. Okay, now which you probably have never seen before doing in basic calculus, but now we're gonna stick the integral in there, but that changes nothing. This integral obviously goes to infinity as x goes to infinity, so that's the thing on the bottom. So we apply the fundamental theorem of calculus and take the derivative of this thing, which equals to what's inside, okay, by the fundamental theorem. And then the bottom also take derivative, we equals to that, and when that cancels out as x goes to infinity, the answer is 0. And that does not have the answer at the back of the book, but I have it plotted out right here. Okay, let's see, problem 12. And I will show you problem 12 right here on top. See, that is, as you can see, the Desmos calculator is able to plot the definite integral formula. You can just type the whole thing in there. Look at that. Okay, and it knows enough that's a function of x. Isn't that cool? And that is such a smart thing. So anyway, as you can see, the integral over all that stuff, it does approach 0. As x approach infinity, it approach 0 a bit slowly, but it does get there, right? So that's good. So that is problem 12. And also within problem 12, you notice the function, there's the function e to the power minus x squared in there, is down here. And I want you to remind you what this function looked like. It looks, and you might think, see, that this function happened to look like this. And oh, I forgot to mention that to type the integral sign in there, you just type in the letters int. It will immediately turn into the integral sign. And then let you input the limits, the lower and upper limits, the 0 and the x, all that. So it's Desmos is a very nice calculator. Anyway, so I want to remind you that this is what e to the minus x squared look like. And you might wonder, and why do I need to know that, be reminded of this? No reason. I just think this function looks very nice. And look how beautiful it is. You know, it goes up smoothly and then come right back down. And then it goes, it's 0 all the way from negative infinity, right? And then when it gets to about 2, it suddenly goes up and then down, and then it's 0 again forever. And I just think that's such a nice function to be able to do that. And so that's that, okay? That's problem 12. Problem 13, let's see, all right. So there is problem 13. We have a similar problem, which, and we will do it in a similar manner. That is, so we have the integration. So we have, I think problem 13, I didn't bother integrating or something. And because I just, being that everything is positive, I just slapped on the absolute value. It has absolute value in it. So being that, then I just say that it's less than or equal to this function right here, right? And being the sign of t is absolute value is less than 1. And then I use the L'Hopital's rule on this thing, which give us, being that this is, now did I, well, whatever. And let me think, and before I say anything else. Yeah, I didn't write it down, but this is an infinity over infinity situation. This will go to infinity as x goes to infinity, and of course x also will, so there's a division going on. And so we take the derivative by the L'Hopital's rule and by the fundamental theorem, then that becomes natural log of x. The bottom stays, wait a second, what? Give me a second here. Sorry, I made a mistake there. Okay, there is this is wrong. The stuff I showed you a little earlier, all this stuff is wrong. So please ignore that. So what happens is, so the limit of this thing is it is infinity over infinity. And that is this, the integral goes to infinity as x goes to infinity, and of course x goes to infinity. So it is an infinity over infinity situation, which means we can apply the L'Hopital's rule, take the derivative, which give us, end up with having sine x in absolute value over x squared as x goes to infinity, that will go to 0. So my result, I lucked out and got the right result, so I didn't even see that I made a mistake in there. But anyway, it does go to 0, so that's that. And I have the graph. I did check with the graph to make sure that I was right. So, but I didn't notice that my process was wrong. So even though I got the right answer, I was still wrong. Anyway, see here. We have here's the problem that I plotted into the calculator, and you notice that it does go to. Sorry, what am I talking about? That's problem 12. I'm talking about problem 13, right? Yeah, this is problem 13. Again, problem 13, I was able to plot it into the calculator. Look at how smart it is. It's able to do absolute value and everything. So I plotted this thing into the calculator, and as you can see, it does approach 0 as the numbers get bigger. So that is anecdotal evidence, I guess you can call it, that it does go to 0. And however, my process was wrong, what I wrote there. And so that's problem 13. The problem 14 is the exact same problem, except that it's going to 0. What happens when the function goes to 0? Where does it go? And as you can see in the graph, it doesn't converge at 0. Okay, so the limit does not exist. And we can prove it by, let's see, I wrote down the proof here. This is a 0 over 0 situation. Actually, this will not be a proof. Let me think. So the problem 14, it is a 0 over 0 situation, so then we take the derivative of it. The problem is the derivative is going to converge at plus as x approaches 0 is let me think. Yeah, the derivative is plus or minus 1, right? Because x is out here. No, we have another x. It should be x squared. Well, let me finish this section in the next video, okay? Because I'm really due at lunchtime, and this video is running longer than I expected because I'm running into unexpected problems. So let me finish this in the next video.